Yes, folks. Hello and welcome to Chem 3. Today we're going to look at this question here. This is a public stream because we were having problems with setting it up privately, like with the link. So that's why this is public. But just to let me know that everybody's there, go to Google Hangouts, please, and then let me know what you're seeing. Because I actually have my camera turned around the other way, so let me know if you're seeing me and the question, please. Waiting for your responses. Right, are you hearing me properly? Who's that? Sandeep, are you guys hearing properly and everything? Great, it's working fine. So we are going to go ahead then, and the plan was to actually go over your mock exam questions, but I realized I only have those as hard copies. So in place of that, I'm going to, I've looked at the multiple choice. I'm going to upload your marks later on back, but there are certain questions in here that I want to go over for about 10 minutes, and then we'll transition and do some other things. I'll talk about your marks, give you guys some work to do on your own. We will be continuing to work like this. As far as we know, the IB exam is supposed to happen until we hear something further, so we'll keep working with the time that we have left. So let's start with this question right here. Using Google Hangouts, we're looking at number 9. I want to see you guys go on Google Hangouts, and it's okay if other people type the answer in, but what you think the answer is, you put that in for me on Hangouts right now, and then we'll discuss the answer to this question. Oh, the question is not clear. Okay, so let me go around and see what the question is looking like. So how is that? How is that for the question? Right, you can see it. Which equation represents the standard enthalpy of formation delta HF of tetrachloromethane? I've been looking over the SL exam, and there was a similar question to this one. It wasn't asking about the standard enthalpy of formation, it was asking about the bond and enthalpy. And there's a difference between the two. That's what I want to use this question to highlight. Okay, so any comments that you guys have, you can put it there. Now, do I know that I can do this in Zoom, or I can do this in Meet, or I can do it as a right here in Hangouts? Yes, I know that. But when I do this as a stream, I can go on. I don't have to bother to save it. It's going to get saved right on YouTube. Then right within YouTube, I can edit it and post it for you guys to look over it, or for the other class, without having to save it anywhere. It would live on YouTube. So that is why I'm posting it here. And then, of course, for the future. And for all of the other students out there who might decide they want to join us as we go up towards the IB exam, it would be very interesting, because we would want to see if we can not just help CIS, but open our classroom to the whole world here on YouTube, and of course on Chem 3. So let me see some answers, please. Who is saying I think it's C? Sandeep. So I see you have carbon as a gas, Cl2, but as a gas, and then you get CCl4. That, I believe, Sandeep, is the correct answer. Anybody else, anyone out there disagrees? Someone saying it's D. Let's go back and see if it's D. Who's saying that? Another person saying C. Human, you are saying D. Yes, now looking at it, I can see why you are saying D. Right? Now I want people to reflect on that. Why it's not C? I'm going to say it's not C, and I'm going to say it's D. And I don't want to give the explanation. I want maybe in the chat for people to answer and tell me what it is. And I want you to reflect on this here. Enthalpy of formation. And what does that mean? What do you know about the things that are going to form the product? What state do they have to be in? That's the answer I want to get. What state do they have to be in? Now, I haven't taken attendance yet for the day, but this is like, I need to see everyone participate in this chat. That is how I'm going to take attendance. Later on, I'm going to give another activity, but initially, this is how I'll be taking attendance. Yeah, I'm seeing, who's that saying liquid there? Viru. Yes, Viru. So this product is in the liquid state. That is how it actually exists, tetrachloramide. But on this side, you're seeing two other hints also as well. What are the important hints on this side? And it relates to the enthalpy of formation. Right, who is that? Sandeep, you are saying they have to be in the standard states. Yes, so initially you selected this one, Sandeep, and upon reflection you realize it's this one. And this is really what I want you guys to do as you prepare for the exams. And you use a multiple choice paper. You realize that D is the answer, but if you don't annotate and you don't put some information saying how you arrived at this answer D, what notes you want to make, because this very same question could be different if it asks about the bond enthalpy of this thing. And if it's asking about the bond enthalpy of this thing, tetrachloramethane, then this could be a valid answer, that you break it up into this. When you break it up into this, you would get the bond enthalpy of it. Okay? So the enthalpy of formation is carbon's got to be in its natural state, Cl2 has to be as a diatomic gas, and then CCl4 tetrachloramethane has to be a liquid. Okay, so any questions on that? Why would not be 4Cl? Who's asking that question? No, they don't have to be in the same states, Bhavna. They have to be in their standard states. So Cl2 must be in the gas, it's Cl2. Carbon, standard state of getting carbon like charcoal, graphite, diamond, whatever, always a solid in nature. Cl2 doesn't exist as a Cl atom in nature, it exists as Cl2 in nature. And then CCl4 is the liquid. Yeah, and this is a balanced equation. 2 multiplied by 2 is 4. You can't go with this because chlorine doesn't exist as this, if that's what you're asking. But that is what you must do. You must not just focus on getting the answer, but understand why you dismiss the other three. Yes, so it is going to be D. It is going to be D. Okay, so let's move to another question. Okay, so I'll select another question here for discussion. Any other questions that you have? Just put it there in the chat and I will see it. Okay, first let's find out if we can see this question. Here, let me have a look. Yes, guys, so this is live on my YouTube channel. You guys are the first time ever that I'm actually doing this in the history of my YouTube channel. The other classes and of course, we don't have to go this way. It's just a chance to go and for me to explore another way and to see how it works. And there's some reasons why. This can actually go on like this for some time. I can easily record it and save it. So it's something that I'm looking to do next. Okay? So let's talk about this question. Which molecules react to form a dative covalent bond, which is in older exams it would have been referred to as a dative covalent bond, but now we refer to it as a coordinate covalent bond. And this question actually links to a whole lot, not just for SL but also for HL. So I want to engage you guys in that discussion here with this on the chat. But first, let's try to figure out what the answer is. So let's get some people saying what the answer is on the chat, so I can then discuss it here, what you're saying. Make sure you can see it. It's number 13 that we're looking at. Okay, yeah, we have Hyungmin saying C. We have a couple of C's and a B and an A. Okay, I'm waiting for some more answers. Okay, I'm waiting for some more answers. There is a chat open on YouTube as well, but I'm not engaging myself in that. If anyone's typing in there, I'm not there. We're in our private Google Hangout. Okay, so lots of people have chosen C. Now, coordinate covalent bond. What are you going to look for? If for something to engage in coordinate covalent bonding, it must have something present, and it must be able to have something present, and the other thing that is going to bond with it must be able to receive that thing that it's giving it. Okay, so it's a pair that they're looking for. Which molecules react? So one of them is going to have something to plug in, and the other one's going to have something to receive. What is the plug-in item that's needed? Yep, the electrons come from one atom. The electrons come from one atom, but that one atom that's giving the electrons, we would call those two electrons something. HL students, you should be quite familiar with it, in fact. You would call them something. That pair of electrons that would be given. Waiting for a response. I'm seeing nucleophile, yep, I'm seeing lone pair, and all of those are the words to use. Because ammonia is very much all of those things. It's got its 3 hydrogen atoms. It's got its lone pair here. Again, once we start this discussion, once you are writing these notes for yourself next to a question, you shouldn't just confine yourself to this. Especially HL students, you should know these two, and then you should immediately be thinking about what else that connects to. What topic and what else that connects to. So an HL student, maybe you can tell me what this connects to besides these two terms. Lewis bases. Lewis bases. So right away here you have an example, of course, of your classic Lewis acid base pair. This is straight out of the textbook, where you have, actually in the textbook we have BF3, here they have HF, but ammonia has its lone pair to give, HF has its lone pair to receive. So HF could be described as an electrophile. Ammonia could be described as a Lewis base. HF could be described as a Lewis acid. But HF could also be described as a Bronsted-Lowry acid, because it does have a proton here that it can donate, so that makes it a Bronsted-Lowry acid. Ammonia could also be described as a Bronsted-Lowry base, because it could possibly receive an H+ to form NH4+, the ammonium ion. So it's not always that something would be both a Bronsted-Lowry acid and base at the same time, a Bronsted-Lowry base, and a Lewis base at the same time, but it could happen. And here is such an example. If I change this to BF3 though, then we would have something that could receive a lone pair, and if it could receive a lone pair, then it would become a Lewis acid. This specifically for HL. It would become a Lewis acid because it receives that lone pair, but it won't be able to donate a proton, so therefore it won't be a Bronsted-Lowry acid. Any questions or comments on that? And if you're hearing everything okay, so this is related to all of this here. And there's one word also especially for HL students, that we should also connect to this, and begins with L. And it's related to topic 13 with colored complexes. This can also work. Anything that can do coordinated covalent bonding is also going to work as that L word. What is it that bonds to those things that we discussed in topic 13? Yes, the ligand, Garima, the ligand. The ligand is the thing that has the lone pair. But ligand is also a nucleophile. It's also a Lewis base. It's all of those things. And depending upon what ligand you have, what is the effect on the transition metal? Why is it important to know what ligand you have when you are studying transition metal complexes? Why is it important to know what ligand you have? Now, the question is, can a resonance structure be described as something that alternates between two structures? It doesn't actually alternate, Nandini. It doesn't actually alternate. What it is, let's take this as an example. And the term resonance, like I mentioned in class some time back, it's an unfortunate term. Because in physics you hear about a wine glass resonating with a certain frequency of sound, and that's a vibration that you're immediately connecting the sound wave matching the natural frequency of the wine glass. So when the term resonance is used in chemistry, it's natural to believe that there's a movement back and forth like this. But the better term really is to call it a hybrid or a resonance hybrid, but I would even recommend to leave out the word resonance from it because the true structure of this, the data on this molecule shows that ozone doesn't have any double bonds. Bond strength is never double bond. It doesn't have any single bonds. Bond strength and bond length data show that it's made up of 1.5 bonds. But that is a separate and apart question from this. But I know you asked the question, and we're here for our personal business as a class. Whatever else is happening on the stream, for anybody else, that's an addition. So my original question was this L word, and did someone say what it was? The thing that gives its covalent, its lone pair to form a covalent bond. Right, looks like no one knows the answer to that, or no, some people are lost. It is a ligand. And you have the spectrochemical series where you study about ligands, the strongest ligands and the weaker ligands, and the only type of complex that we are studying about in HL chemistry is the octahedral complex. Okay? But this stream is for everybody, so we won't want to focus too much right now on HL chemistry. So I'm going to move to one more question, and then I'm going to end the stream for today. Because we'll consider 3 questions at a time, because this is what we are, Chem in 3. So 3 questions at a time, and then we'll shut down the stream and start again some other time with some more questions. So let's go to our 3rd question and last question for this live stream. Okay, so we had a question about resonance structures a little while ago. So take it that everyone can see this here. Let me know. Right? So this is the question that we have in front of us now. Yeah, people are still writing in about the last question. And if you have any questions about that, you can ask. But this here, which compound has resonance structures? So I see someone's quickly put in A. Nandini, no, that is not correct. Why are you writing bromine? Benzene. Oh, yes, Nandini, but look carefully. Don't be so quick to click on things. Is this really benzene? C6H12. Yes, it's not. It's hexane, cyclohexane, Viru, cyclohexane. C6H12 as a straight line molecule would be hexene. But if it's like this, there's no unsaturation. So the index of hydrogen deficiency of this will be 1 because of its ring. It doesn't have any actual unsaturation by way of a double bond. What C6H12 is this. And it's bringing me to discuss a few other things as well. Right? It's very possible for me to discuss this whole chemistry course by going through just 100 multiple choice questions and adding additional discussion. Like here, I'm going into this additional discussion now. This is cyclohexane. There are no double bonds in this system at all. So therefore, you're not going to have any resonance structures. Looking at it like this, like Nandini did, and thinking, oh, it's benzene, is why it's put there as a distractor to catch you making that error. So you don't want to make that error. You want to practice with these questions. While we're on this though, I want to point out that this is not cyclohexene, it's hexane. It doesn't have any double bonds, but it does have the formula of the same general formula, or the same, actually the very same molecular formula of hexene. Because if I wrote out hexene as a straight line structure, 2, 3, 4, 5, 6, then I decided to put in a double bond here. 1, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This would be C6H12 also. This would have 1 point of unsaturation. So it's IHD, by the way, which is another topic which I'm relating now to this question. The index of hydrogen deficiency is 1. Here too the index of hydrogen deficiency is 1. Not because of a double bond, but because of the presence of a ring. This IHD is 1. So while our textbook does give a formula for calculating the IHD, in exams really, the main thing to be aware of is that double bonds count for 1 IHD, triple bonds count for 2, and rings also count for 1. So if a structure has 1 triple bond, 1 double bond, and 1 ring, then it would have 2 plus 1 plus 1, 4. Its IHD would be 4. But let's get back to the answer for this question. What are we going to be looking for in a resonance structure? Let's see what answers people have put up. Yes, Viru, I hope you are watching what I'm saying here about all of this, right? Why this is cyclohexane. This doesn't have any double bonds, and the alkenes have to have double bonds in them. Okay? But let's get back to this question here. What we're searching for is which of these structures has resonance in it. So I want to see some people give me some answers. And then if you want me to go over any of these other things for the day, we can also bring that up before we close this part of our class. And then we will go into our private chat on Google Meet. Yes, Viru, no one is expecting that in the exam. Whether this is hexane or the ring structure, whichever one it is actually, it could be that one as well. So I see that point that you're making it, so it could be that one, so then that would make you right. But the reason I went down into that angle of thinking is because Nandini said this was benzene. So that's why. But now that you bring it up, yes. But no need to distinguish which one it is. Because if it has a double bond there in that one place, that double bond is not going to be mobile. You have to have a system where the double bond could actually be represented here like this, or here like on this side. And I don't want to say it's mobile, but this is a possible structure, and this is a possible structure for it, for the same molecule. And the true molecule is really this. That doesn't happen when you put a double bond in an alkene like this. When you put in a double bond and you have other carbons like this around, this double bond, it does not move from one place to the next. And all the evidence shows that it has a double bond and it's made up of other single bonds. So therefore this doesn't have any 1.5 bonds, but this does have a 1.5 bond. One of these structures here would have a system like that, and we're not really concerned too much about the sodium. If we drew out the carbonate ion, then you would remember what's going on with that. CO3, 2 negative. This is straight out of the book, and this is a classic one in the exams, that the carbonate ion is an example of something that shows resonance. The experimental data would show that the bond strength in here is not really a double bond, but what you really have is a resonance structure that's made up of the double bond resonating, and so you have 4 bonds divided by 3. Each thing has a strength of 1.33 bonds. That's what experimental data would show for this. And you don't really have a double bond that's at any point in the structure. So resonance structures don't move from one structure to the next back and forth. But the experimental data shows that the actual thing is an intermediate. It's just a way of representing it in books, that we put one structure here and then we put an arrow like this to represent resonance. Okay, so let me see. I see Viru has typed something. Do chiral molecules sometimes have bonds that have confused scientists whether they resonate or not? Well, my answer to that would be no. Chiral molecule, what is it? It's one that has carbon that is attached to 4 different groups. And this is a separate issue from resonance. Having 4 different groups attached to it, then you have, this is your chiral carbon, your asymmetric carbon. It shows optical activity. What we mean by that is that if we constructed its mirror image on this side, that the 2 mirror images would not be superimposed upon each other. This is where the term chirality comes from, that you can't put one of your hands over the other one like this. The term chirality means handedness, so therefore that is, this is a separate topic from that. While you might have a resonance structure in something that's chiral, that is, I think, beyond the level of our course to examine molecules to see whether that is true or false. So we don't need to go into that. Okay, so I'm going to stop this now, and then we are going to go on to Google Meet. I'm going to send you guys a link here. I know we can chat right here on Hangouts, but the system on Google Meet is a lot smoother, so we will go there, and I will meet you guys in a few minutes. So I'm going to turn off this stream now.